Welcome to The Explainer. Today, we're diving into something that's honestly a bit terrifying if you work in ML, the silent killer that causes perfectly good machine learning models to just die in production. Building a model is really just the starting line. Keeping it alive and actually accurate out in the wild, well, that requires a totally different kind of engineering. Consider this idea for a second, because it hits the nail on the head. Imagine you've got this slick fraud detection model. You deploy it, and it hits 94% accuracy on day one. Everyone's high-fiving. But fast forward 6 months, without you touching a single line of code, suddenly more and more fraudulent transactions are just slipping right through. The crazy part is that no errors are thrown, no alarms are going off, the software hasn't crashed at all, but the model itself, it's silently become completely wrong.
So how do we stop this silent killer? Here's our roadmap for today. We're going to break down the 3 types of drift, how to detect them using Evidently AI, how to move from basic reports to full automation, building out those self-healing pipelines, and finally wrap up with some crucial production best practices.
All right, Section 1, the 3 types of drift. To really understand why models degrade in the first place, we have to remember one key thing. A trained model basically freezes a relationship at one specific moment in time. But the real world, it just keeps moving right past it. The first way things break down is data drift, sometimes called feature drift. This happens when the actual distribution of your inputs changes. Think about it like this. Maybe your core customer base just naturally ages from their mid-20s into their 40s. We all get older, right? But your model doesn't know that. It's still making decisions based on inputs it literally never trained on. The good news here, this is actually the easiest drift to catch, because you just need to compare the input data distributions. You don't even need the ground truth labels yet. Next up is concept drift. Man, this one is way stealthier. In this case, the inputs look exactly the same, but their actual meaning or their relationship to the outcome has completely shifted. A perfect example is when fraudsters invent totally new tactics to bypass old patterns. To catch this, you absolutely need the ground truth labels, which, let's be honest, often arrive weeks or even months too late. The third type is prediction drift. This is when the distribution of the model's own output just drastically shifts. Let's say your model usually predicts a 5% customer churn rate, but out of nowhere, it's predicting 25%. That massive jump, that's a giant red flag telling you something upstream is fundamentally broken, and you need to investigate it immediately before you even think about trusting those predictions. Moving on to Section 2, detecting drift with Evidently AI. So now that we know what we're actually looking for, how do we catch these drifts in the wild? Well, for that, we're going to look at an incredible open-source Python library called Evidently AI. The core engine of Evidently works by constantly comparing 2 distinct datasets. On one side, you've got your reference data. That's usually the baseline data your model was originally trained or validated on. On the flip side, you have the current data, the stuff your live production model is seeing right this second. Evidently runs rigorous statistical tests across every single feature to spot the exact differences between these 2 worlds. When it runs these comparisons, Evidently spits out 3 incredibly useful things. First, visual reports for your engineers using statistical methods like the Kolmogorov-Smirnov test so you can literally see what changed side by side. Second, it creates these binary pass-fail test suites designed specifically to plug right into your automated pipelines. And third, you get monitoring dashboards so you can track these metrics continuously over time. Now, here is the absolutely crucial part, this default threshold of 50%. If more than half of your individual features have drifted, Evidently automatically flags the entire dataset as drifted. It gives you a single simple Boolean value, true or false. And that is exactly the trigger we need to automate our system's response. All right, Section 3, from reports to automation. Let's look at how this whole thing evolves from a pretty visual report for humans straight into a hard, machine-readable test suite for our actual infrastructure. The cool thing here is how we can set these really strict less-than parameters using an LT variable. By setting these rules up, the suite basically acts like a binary pass-fail unit test for your live production data. You can demand that less than 50% of columns drift, or ensure a highly critical feature like, say, average spend pulled from your Feast feature store remains perfectly stable. If a test fails, boom, you have a definitive signal ready for automation. Now, tracking input data is a fantastic leading indicator, sure, but eventually your actual ground truth labels are going to arrive. When they do, You use Evidently's column mapping feature. This explicitly maps the actual, real-world outcome right against your model's prediction. Evidently then calculates the true drop in accuracy, precision, and recall, so you get a direct mathematical measure of just how much your model has actually degraded.
Which brings us to Section 4, building self-healing pipelines. Because here's the thing, catching the drift is honestly only half the battle. The real magic, that happens when we connect this detection directly into our retraining architecture to close the entire MLOps loop.
This is what a true self-healing system looks like in action. When the Evidently test suite fails, it automatically triggers a Kubeflow pipeline. That pipeline instantly pulls fresh features from the Feast store, retrains the model with full MLFO tracking, passes it through a strict evaluation gate, and, if the new model is actually better, deploys it straight to Fast API. A degraded model goes in, a healthy model comes out, and the best part, it happens with zero human intervention. So how does this whole chain reaction start? The entire self-healing check runs quietly in the background as a Kubernetes cron job. Every single morning, bright and early at 6 a.m., it wakes up, pulls the latest production data, and runs that test suite. If the real world has drifted too far from what the model knows, it issues that fail signal to trigger retraining. Your model can never silently die because something is literally always watching it. Finally, Section 5, production best practices. Before you rush out and implement this self-healing architecture, we need to talk about a few hard-earned war stories you absolutely need to follow so you don't accidentally trigger a total disaster. First off, you must pick your baseline reference data deliberately. It needs to be what the model actually trained on, not just some random recent window. You've got to monitor inputs constantly and track performance the literal second labels arrive. Also, tune your thresholds to match the real business impact. A high-stakes fraud model needs a way tighter leash than a movie recommender system. Always let your human team know when an automated retraining happens, and most importantly, never, ever remove the evaluation gate from your pipeline. You have to guarantee that a newly trained but somehow worse model cannot automatically reach production. A self-healing ML system takes an unknown expiry date and turns it into an automated refresh cycle. By linking Evidently AI directly to a Kubeflow pipeline, we transition from just crossing our fingers and hoping our models work to guaranteeing they adapt, which leaves us with one critical question about your current infrastructure. If your most important production model drifted today, how long would it take your team to notice? Think about that, and we'll see you in the next explainer.